share your screen?
Yeah. Can you hear me now?
Yes, very good. And
Mhm.
I think we're ready to go. So Lingfu is a PhD student at Princeton, and he will talk to us about cutoff transition for repeated averages.
Okay. Thank you, Evita, and thanks a lot for everyone who come to this talk today. So today I'm just going to present a work on a Markov chain, which is called the repeated average. So in collaboration with Shorov Chatterjee, Percy Diaconis, and Evan Sly, we obtain several convergence results for this Markov chain, and in particular, a cutoff transition for this. I need to see before I start that this cutoff is something different from what is usually referred to as a cutoff for Markov chain. So usually for Markov chain, cutoff is just in terms of the total variation distance to some stationary distribution. But this Markov chain is something that's different, that basically is even not irreducible, and almost surely it would converge to some absorbing state. And this cutoff is just in terms of the distance to that absorbing state in the L1 distance, which I will explain now. Okay, so this is a model. So according to Percy Diaconis, this is something that asked to him by Jan Bourgain from the 1980s. So suppose you just have some vector in this n-dimensional space. At some step k, suppose your current vector is xk. What you do is that you just uniformly randomly pick two coordinates I and j. And what you do is that you just replace the number at coordinate I and the number at coordinate j, both by the average of these two. And you keep all other coordinates the same. And in doing this, you just obtain the new vector, which you call it xk plus 1. And then you just repeat this, process over and over again. So there are many motivations to study this. For example, this can be just represented as a sequence of product of a sequence of random matrices, and this models some quantum operators from quantum computing. And they can be also used by economists to study, you have a bunch of people and you have some wealth distribution, and then what will happen if you some average between peoples. And there are also many studies for this from both applied and pure mathematical aspect. Started from the 1960s or 70s, and more recently by people in terms of communications, and studied this under the name of consensus algorithm or gossip algorithms. And there are also many other variants of these models that have been studied. For example, instead of average all the pairs of coordinates, you just work on some general graph, and each edge is picked uniformly randomly. And whenever some edge is picked, you just replace the numbers at the vertices of that edge by their average. And you can, for such a graph, it's like a lattice or just a sequence. This is sometimes also called the local iterated averages. There is also another variant called some defined model, where that the average is only allowed to happen when the number you choose have the difference smaller than some threshold. There is probably another more well-known thing called the Katz work, proposed by Katz from the 1950s, where they use that to model Boltzmann gas, so that this random walk happens in the sphere in this n-dimensional space, such that at each step, two coordinates are chosen randomly, and you just take a random rotation in the plane spanned by these two coordinates. But for all of this, most of the previous results are on some other properties like ergodicity or a spectrum gap, and very few have been known about the decay of this, of the convergence of these things. So let's go back to the model that we are studying. So it is quite straightforward to show that this is actually not irreducible, and almost surely you would converge to a vector where all the coordinates are the same, and the number just equals the average of all the coordinates at the beginning. And then the next question is on the rate of convergence. Something that's straightly forward you can do is that you can compute the convergence, the distance to this limiting vector in the L2 distance. So you can show that the expected L2 distance to the limiting vector just decays by a fixed factor at each step. So it's just like after every average, the expectation decay, like it multiplies a factor of 1 minus 1 over n minus 1. And then you can use this to say that the expected L2 distance to the limit decays exponentially. But the more interesting or more relevant and also more difficult problem is about the L1 distance to this limiting vector. So basically, the L1 distance just describes what's the remaining mass you need to redistribute to reach all like equality. And this is sometimes referred to Hoover index, like in by economists. And for this, we just denote Tk to be this L1 distance at some step k. Then we want to study this decay of this process Tk. And one thing that you can imagine that is that the initial condition actually matters. So for example, if your initial condition is like the mass is distributed already quite like equally among all these coordinates, this Tk would decay very fast. Whereas in some cases, this decay is much slower, and we consider a worst one where that initially all the mass concentrates just on one coordinate and all other coordinates are zeros. Then use linearity, you can show that this is actually the one that decays the slowest in terms of like all the vectors which are non-negative and the sum among coordinates equals to 1. Okay, so now let me just present the cutoff result that we get. But before that, I would like to talk about something that's slightly easier, which is a pre-cutoff. So using this exponential decay of this L2 distance and just a simply application of the Cauchy-Schwarz inequality, you can show that after step n times log n, this thing is already in this little o1 order, so that from that, like the upper bound decays exponentially, like whenever just you increase by the constant times. And on the other hand, you can show that when you are at a step smaller than n times log n over 2, this L1 distance is still very big, actually being close to 2, so that 2 is just the initial value. So this is just because at this time of n times log n over 2, most coordinates have not been averaged with something non-zero. So at this time, most coordinates are still 0. And this is just something you can argue using something called something like a coupon collector problem argument. So you say that there is something that's so that the Tk is very small at n times log n, but still very close to the initial value at n times log n over 2. So this is something called a pre-cutoff, and that usually actually implies there should be some cutoff, but it is still mysterious what's actually happening in this window. So if there is indeed a cutoff, where this cutoff should happen. And this is the main result of us. So we show that in the sense of improbability convergence, there is indeed a cutoff. And this cutoff happens precisely at theta times n log n, where your theta is 1 over 2 times log 2. And we also gain some next level information so that we show this cutoff window is actually has weights n times square root of log n. And you can show that after this rescanning that in this window, the profile of the decay of this L1 distance actually behaves like the cumulative distribution function of the standard Gaussian. So you can see this has a Gaussian cutoff profile. Okay, so now let me just jump into the ideas of the proofs. So this is something that's quite straightforward. Let's look at what's happening. Initially, you just have like 1 and all others are zeros. And you just randomly pick 2 coordinates to average. But what's actually happening is that most likely you just choose 2 zeros. And if you average 2 zeros, you just like change nothing. But with the probability 2 over n, the first coordinate is chosen to average with some other coordinates. So you get like 2 copies of 1/2 and all others are remains 0. And the time to have that happen in expectation, it happens at the step n over 2. And then you just keep doing this so that you wait like in expectation some order n steps. You would have that 1 copy of this 1/2 is averaged with some 0. Then you just get 2 copies of 1/4 and 1 copy of 1/2, and all others are still 0. And what can happen next can be slightly different. In one case, like you again wait like some order n steps, then like this 1/2 is first chosen to average with some 0. Then you just get 4 copies of 1/4 and all others are still 0. But there is also another possibility that 1 copy of like 1/4 is chosen with some zeros. Then you just get 2 copies of 1/8, 1 copy of 1/4 and 1 copy of 1/2, and all others are still 0. But there is actually one more possibility. So this 1/4 and this 1/2 is chosen to average, and then you just get 2 copies of 3/8. But I would like to say that this the third scenario is something that's quite unlikely to happen. This is basically because you only have 3 numbers that are non-zero, and the probability that you choose 2 numbers that are non-zero to average is in the order of 1 over n squared, whereas the other 2 possibilities happen with probability in the order of 1 over n. So this happens with a lower order probability, so we can just assume that this actually does not happen. So now we just use this tree structure to model this. So initially, you just have a mass at the root with mass 1. And then with rate 2 over n, it just splits and becomes 2 particles with mass 1/2 each. And each of these particles just independently splits with rate 2 over n into like 2 with like a mass 1/4. And then you just let this happen, and so that each particle splits with rate 2 over n independently into 2 particles with a smaller order. So this gives rise to this repeated average, so that at any time, like each particle at level I just corresponds to a copy of 2 to the minus I. And this happens if we just require that all the averages only happen between a non-zero number and zeros. So you just prohibit all the averages between 2 non-zero numbers. And in that case, like all of these numbers can just like split into 2, and all of the numbers are just some non-positive power of 2. And this would be good until a critical level of log 2n. Basically, at level log 2n, there are just n particles. And for any particle, that the time that it takes to reach this level is in this order. And this is basically because if you just look at some node at this level, and then you just have a chain to the root with length log 2n. And in this chain, you just see some particle that jump from the root to the leaf. And the waiting time at each step is something has expectation n over 2. And the waiting time at each step are independent. So just using the central limit theorem, you have that the waiting time for a particle to reach a specific node at this critical level is in this order. So let's analyze what's happening. So slightly before this time, you will see that most of the particles are at some level above this critical level. This means that most particles would have mass greater than or much greater than 1 over n. This means that in your repeated average, most of these coordinates that are non-zero would be much larger than 1 over n. Then since the total mass is always 1, you would see that most of coordinates are still 0 at this time. So this has 2 implications. The first is that this L1 distance is still very close to 2. And the other application is that this tree is still a very good approximation up to this time. Basically because up to this time, like most coordinates are 0. So it's on average very unlikely for 2 coordinates that are non-zero to be chosen to average. So our assumption that all of these averages happen between coordinates that are like 1, 0 and 1 non-zero, this assumption is still valid, at least in an average sense. But things can be different starting from this time, critical time. At this time, now most of these particles are in this level log 2n. So most of these weights are on coordinates that are roughly in the order of 1 over n. Then you can show that just direct computation that the L2 distance to the stationary now is in the order of 1 over n. So if you just run some big constant times n more steps, you would just get that using the exponential decay of the L2 distance, the L2 distance is now like little c over n. Then use Cauchy-Schwarz, you can show now this L1 distance is a very small constant, like little o of 1. And this with what has been said slightly before this critical time, we established that there is actually a cutoff. And more careful analysis gives this cutoff profile using the same spirit of things. And that's it. Thank you for your listening.
Let's all thank Lingfu. Are there any very, very quick questions? Like we have 1 minute. Well, actually, yeah, let's go ahead.
You have one very special x0. What happens if you start with a very general x0? Does the cutoff change, and can you understand what is exactly the value of the cutoff given any sequence x0?
You mean like the initial condition is
yes.
like yes. So that actually you can use the same way. So that first is like much that should be faster than this, and using just like because this model is linear, so you can just write that thing as a linear combination of like starting with different like 1 zeros for 1 at different coordinates. And on the other hand, like if you want to get really careful analysis, you can actually just map that thing like to this tree. So it's just like initially you do not have a mass at the root, you just have mass at many other places. Then you can use a similar way to actually analyze like the decay, and you can basically just get the profile. And actually, you can just cook up like whatever kind of profile you want, just using by like take different initial condition, which this corresponds to different initial configuration in this tree. Yes.
Perfect. Let's thank Lingfu again, because now it's time for Xuanping's talk. And we can ask Lingfu more questions after Xuanping's talk at the lunch break, so we can all stay.